Okay, so this is a joint work with Zongren Zou, Jerome Darbon, and George Karniadakis from Brown. So it's my former colleagues from Brown. Zongren will be on the job market this year. Yeah. Okay, so today I have two goals. Firstly, although some of you may have heard about this, this work for many times, I've presented for many times, I feel it's not so clear. So I reformed the pitch part, the first part of the talk. Hopefully this time will be more clear. This is my first goal. And second goal, I would like to advertise a little bit about me and my research so that there may be still some further discussions, scientific collaborations, and so on in the future. Okay, so let me talk about my motivation from machine learning. So some broad view about how to do the method design in the machine learning. So we start from scientific computing or real-world problem. When you are given such a problem, firstly, we do the modeling. We get a learning problem or an optimization problem. This is more at an abstract level. There is no neural network here at this stage of modeling. And then we get such a minimization problem where you have a function or an operator as the variable, and you design some loss function to minimize. And then we introduce neural networks and all those Monte Carlo sampling for approximating some integration in the loss function. And then after this step, you have some minimization problem in a finite dimensional space with the neural network, everything involved. So this is the big framework, how we design neural network method. And there are two steps. In the first step, we do the optimization-based modeling at an abstract level. It's a little bit different from how traditional modeling we did in the applied math history. For the traditional level, we prefer to use some equations, PDE, ODEs to do the modeling. But after a while, when we have AI, we prefer to use optimization. So we shift from equation-based to optimization-based. And at this stage, there may be some good theoretical analysis can be done with this optimization process, because sometimes this loss function may have some convexity, nice structures, and then you can do some analysis here. And then a key point of this stage is we need to design the variables, which should be a function or some operators or more general things. And then we should design a loss function. By minimizing the loss function, you should get the solution to the problem that you want to solve. And there are different types of problems, and people have already designed different types of problem structures. For instance, the most straightforward thing is function or operator fitting. If you already want to fit some function or some operators from data, it is the most straightforward way. You use least square fitting. And if you want to solve a sampling problem, then people design generative model to handling this, to have this minimization problem. And then more broadly, if you want to combine several problems to increase data efficiency to such that they can learn from each other, you want to use one neural network to solve several problems, then we use in-context learning in this loss structure. And then, or if you want to solve for some black box optimal control problem, you want to find a good policy, but you don't have the model for your environment, then you use reinforcement learning here. Okay, and for the second stage, now we have the neural network design. Now we have the neural network structure at this stage. Now things are become more complicated. We need to design the neural network architecture that is related to how expressibility your model is, model expressivity. And then you need to design what kind of data you use. This is related to data efficiency, how to increase the data efficiency. And then for the training process, this is related to trainability, how easy it is to train your neural network. And then in this area, theoretical studies are much harder, I guess. And there are some theories done in this stage. For instance, universal approximation theory for the model architecture part, scaling law saying that's how your error or your computational cost scale with respect to data and architecture size. And also loss function landscape can help you to understand how easy it is to train your neural network. For this talk, I will focus on the first part. I will not touch the dirty work on the neural network side. For the first step, we have some very popular models, such as generative model. We have diffusion models that we have heard a lot for a lot of time. And then optimal control is also another thing that is highly hiddenly related to some neural network thing. And then in this work, I try to use log transform, which is a mathematical transformation, to connect between the generative modeling with optimal control. Although I didn't use reinforcement learning, but using this connection can lead to many, many open doors. And now my motivation is different representation formulas of the same problem will provide different machine learning methods. For instance, if you want to solve HJB equation, you can use equation itself to design pin loss, although we don't like that. You can use some characteristic line method like Stan presented, the work with Yasan, to have this special loss. Or you can use a grid-based scheme to design the loss like Richard Tsai did in his paper. So there are so many different, or you can use optimal control framework, optimal control loss to solve HJB. So many different ways to express the same problem. Different ways will give you different machine learning method. And then you have a lot of tools to choose depending on where your difficulty is, then you can design your own method. So my motivation here is try to get the connections between different representation formulas so that you have the doors open to different machine learning methods. Okay, so now let's go through a little bit more details about the techniques that I will use in my talk. Firstly, diffusion models. We have seen similar figures for many times. We know that there is a forward process that generates data, adding noise to data, and then you have the inverse process, reversed SDE to, when you do the inference, you introduce this score function inside the SDE so that you can somehow do the denoising starting from the noise and gradually get a clear image. So this is how diffusion model works, and now this is the key points that all of us have introduced again and again, this score function. People observe that the score function is the really important thing that people use at neural network to approximate the score function. Now, actually, Marcus has mentioned this in his talk, and I want to mention this again, emphasize this again. The score function that people approximate in the diffusion model is actually the same as optimal control, or what Marco said in some midfield games problem, the control in the midfield game problem, or optimal control in some problems that I will show you later. So with this log transform, you can see how the score function is related to the optimal control problem. So this equality sign is the key point of my talk. Now let me introduce what is the log transform. It is a more general case, the more general transformation of Cole-Hopf transform introduced long time ago by Fleming and those large division principle people. So it is a transform between some linear system with a nonlinear system. The linear system is usually studied in some PDE theory related to the probability theory. The nonlinear system, somehow surprisingly, related to optimal control. So in this way, the PDE theory, some probability theory, and optimal control, they are all connected to each other. Now let me give you a easy example using Cole-Hopf. So what do I mean by the linear system, the nonlinear system, and how they are connected? So for the Cole-Hopf formula, the linear systems are two heat equations. Although when you see the Cole-Hopf formula in PDE theory, sometimes you only see one heat equation and one Hamilton Jacobi viscosity Hamilton Jacobi PDEs. But here I would like to put two equations, and then you will see later that the Cole-Hopf transform we usually mention is only one part of this connection. So when you have two heat equations, mu and nu, and then you apply this log transform to one equation mu, get a new function s, and then you multiply those two solutions together to get a function rho, and after you do these two equations, two transformations, you get a coupled Hamilton Jacobi, viscous Hamilton Jacobi, and the Fokker-Planck equation. So, and then this is related to a lot of things that we're familiar with: stochastic optimal control, stochastic optimal transport, Schrodinger bridge problem, and mean-field games, and so on and so on. And the heat equation is also very useful in PDE and in probability theory, and it describes how the Brownian motion evolves, how the density of Brownian motion evolves. So you can see this nice picture. And actually, the log transform is more broader than that. It's not just applied to heat equation. It can be applied to many different equations. As long as you have a stochastic process, you can get a Kolmogorov forward equation and the Kolmogorov backward equation. You put one equation for mu, another equation for nu, do the same transform, and now you get something similar to Fokker-Planck, something similar to HJB. Although the formula here may be different from the original Fokker-Planck, original HJB, but there is still some connection like this. And then the Kolmogorov forward equation, backward equation is related to, they are related to evolution of some stochastic process, not necessarily Brownian motion. You may have some jump process, Levy process, and the random walk, a lot of different stochastic process here. And also, surprisingly, you also have this connection to stochastic optimal control Schrodinger bridge problem. But if you change the resources of stochastic process from Brownian motion to some other like jump processes, this stochastic optimal control, the stochasticity may be different from the stochasticity we are thinking about in the mean-field games. You may not have Laplacian term, you may have other terms, but there's still some stochastic process on the line, and it's still a control problem. And now you can see this is a nice picture connecting all the like key points together. You have PDE theory, you have differential equations here on the left-hand side. You have this evolution of stochastic process from a machine learning perspective that is connected to diffusion model, which is a very useful tool. And then you have this optimal control, mean-field games, and everything that we care about here. So in this way, the log transform gives you a good tool to connect all those things together, so that if you want to solve some problem related to any block here, then you can have a bunch of different ways to represent this problem, and then different ways may give you different neural network or different even traditional non-neural network methods. Okay, so you may have diffusion models here. You may have some traditional PDE solver here, or you may use a physics-informed, type of neural network here. From the numerical perspective, here you have numerical PDE. Here you have generative AI, some probability algorithms. Here you have the solvers in control, in optimal transport, in mean-field games. So you can they are like building blocks. You can plug and play. Some more abstract level, some more details, what I was talking about is, if you have the Brownian motion case, you have heat equations here, you have Fokker-Planck here, viscous HJ here, but it works for more general process. For a very abstract operator A, you can have similar things, and the whole connection still works. And this is not something new. It's already studied a lot in large division principle or other areas. This is like an illustration. So remember, we have two equations, mu and nu, in the linear system. We have this rho that solves the Fokker-Planck equation. The idea is if you solve the first equation mu backwardly, and if you solve the second equation nu forwardly, and if you multiply them together, you get the solution to the Fokker-Planck equation. And what is in the diffusion model is you don't have the second row. You have a constant function 1 as the second row. So that means mu times 1 equals rho. That's why you have a backward system, and then you have a forward system. They match each other. This is how diffusion model works as a special case of this log transform. Now, let me go to more about the diffusion models from this log transform perspective. So in the log transform perspective, you have two equations in the linear system. You have two equations in the nonlinear system. They are connected using the log transform. For diffusion model, you have a forward process to generate data. That is somehow related to the first equation in the linear system. And you have the backward reverse SDE to generate samples in the inference stage. The density to this reverse SDE solves this Fokker-Planck. Therefore, this connection happens when the second equation nu is constantly equal to 1. In that case, rho t equals mu capital T minus t times 1. That's why you have this forward and inverse reverse process in the diffusion model. And some bullet points to summarize. We have constant equal 1 as the function nu, and then we have this function rho and mu to be reversed to each other, time reversal to each other. And the most important score function in the diffusion model is actually proportional to the gradient of the solution to HJB. That is our optimal control. So when you take the gradient, if the Hamiltonian is quadratic, it's somehow related to optimal control. So one sentence, the score in the diffusion model is the control in the stochastic optimal control problem. And there are a lot of related works by Ben and Marcus and Sitin and Wu Chen and Stan and some other people. And what is a good thing about this more abstract level of understanding of this diffusion model is this log transform is not specifically to Laplacian. It's not specifically to Brownian motion. It can be more general. You can have more type of stochastic process on the line. So that means for diffusion model, you don't need to add Gaussian noise. You can add non-Gaussian noise. Then the underlying process is not SDE. It can be very general, but the whole thing still works. You can still have HJB, but not not in the same form as the stochastic HJB. Yeah.
What about implementation? I mean, if you do the special case that we do, it's very easy.
Yeah.
But here you're getting crazy equations. So how do you implement them?
Yeah, that's a very good point. It's hard to do the sampling, but for neural network, you may train some neural network to sample a more complicated, stochastic, to sample the V process, for instance, to sample random walk, and then you may use that neural network as a sampler.
Are you getting a kernel like we did for?
Yeah, you get a kernel. But the kernel doesn't have an explicit formula. It's not like Gaussian kernel, you can write it down. The kernel is there, but you don't have a formula. There may be some data-driven way to learn it, but it's just don't have an analytical formula for it. Yeah.
And then there's a link with Wasserstein prox.
Yeah, there is a link to Washington prox. And if you generalize it, you can generalize this Washington distance to like Washington P distance and then more general things.
Did people do that stuff in the old days?
I don't know. I don't know.
There is this book by Peng and Currents.
Yeah.
That where they do this very abstract, they use the issue of sending log transfers, very abstract Markov models, right? Non-Gaussian samples. They have a theory.
Yeah, I learned that from that book. Yes. So.
It's a hard to translate book, but it has all the.
Yeah.
Maybe the tools would be useful to you.
Yeah.
Very interesting.
Yes, definitely. So and now, so you have so many different variations. You can plug and play the noise, the data generation part in the diffusion model. You don't need to add Gaussian. Now you have that may be useful if you have different type of data. If some data are not so suitable for adding Gaussian noise, then you may have diffusion models for that. And then you can also have different versions for diffusion models, like diffusion model with guidance, for instance. If you are not satisfied with the data distribution, you want to add some guide using energy functions, then you can do that. From this perspective, I've already shown you some similar figures like this, but for diffusion model, the first row solving mu is like generating data by adding noise. Mu is the density function of that kind of samples. And solving nu is like nu is always constantly 1 for diffusion model. And then doing inference is like to solve the Fokker-Planck equation, which is rho, which is the first equation in the nonlinear system. Then because of this constantly equal to 1 function nu, the first row and the last row, they are time reversal to each other. That's why in the diffusion model, you have this forward and reverse. And for the diffusion model with guidance, for instance, in this paper of Chen Gu, they also try to modify the data distribution a little bit so that in this diffusion model with guidance, we don't want the nu to be constantly equal to 1. Because this is your data distribution, this is the distribution that you want to sample from. Sometimes the data distribution is different from the distribution that you want to sample from. You want to tilt the data distribution a little bit using an energy function. This is how people, this is why people want to design diffusion models with guidance. But from this perspective, this design is easy because we know the last row is the multiplication of the first row and second row. So if you can write the distribution the guided distribution that you want to sample from to be equal to your data distribution multiplied by some Gibbs measure type of thing, and now you get some information about the second row. You can solve the second row. You can even have some analytical formula for the second row, and then the second row will give you the guidance when you do the sampling. Okay, so that's why using this log transform framework will help you to understand all the things related to diffusion model in an easy way, and then you can plug and play. Now, so far I have talked about all the connections. We know log transform is the key things behind all those connections. It connects the diffusion model with the stochastic optimal transport, stochastic optimal control, and people already use this kind of connection to design diffusion Schrodinger bridge in this paper, or to understand diffusion models using optimal control perspective in this paper. And in our paper, we try to propose a new problem setup using Bayesian inference. This is usually how people start to get confused, so it's okay if the second part of the talk is not totally non-understandable. But as long as the first part of the talk until this point is clear, then my first goal for today is already reached. Okay, so for the second talk, for the second part of the talk, because we need to write a paper, then we need to have a problem set up, and so that we can say that our method solved that problem. That's why we somehow cook up this Bayesian inference problem, and then try to sell it under this problem. But turns out that people are not. Well, this is some problem that we cook up, so it's not a very successful marketing. So for the numerical part of this paper, we designed this Bayesian inference problem, and then we design an algorithm using this log transform called HJ-sampler. Then we use optimal control to solve the Bayesian inference problem. We use the diffusion model to solve the Bayesian inference problem. So let me just do quickly about the problem setup. So it is a Bayesian inference of a stochastic process. We assume we have an underlying process yt, and then this underlying process is a stochastic process. The prior distribution is on the initial state of this process. The observation is at the terminal state of the process. And then the likelihood is given by the stochastic process. Given the observation, given the prior, given the likelihood, we want to do the sampling for the posterior distribution. Put in some more realistic setup, I would like to explain this by saying how to infer the pollution in the ocean. For instance, the prior distribution may be some data collected by the people explaining how the plastic pollution is distributed in the ocean. And the likelihood is how the plastic pollution evolves with respect to time. That is related to how the current evolves in the ocean. And the observation is, for instance, we observe some plastic pollution near California area. And then we want to infer the history. We want to know where those pollution coming from. So we want to infer the history past. This is how we set up our Bayesian inference problem. So why this is related to all the log transform thing that we talked before is that if we set the initial condition to be if we set the initial condition for this mu, the first equation, to be the prior distribution in this Bayesian setup, if you set the initial condition to this rho, to the focal length, to the direct mass at the observation, then using the log transform, solving rho is exactly to solve the posterior distribution. So the whole log transform will give you this connection between prior distribution, observation with the posterior distribution. That means if we want to sample from the posterior distribution, the only thing that we need to is to sample from rho. And sample from rho, we know it's easy because rho solves the stochastic optimal control problem. Sample from rho is just sample from the SDE, the controlled SDE. As long as you know what is the control, then sample from this control SDE is not so hard. Okay, so this figures is what I've shown you in the previous slides. But for now, it has different meaning. If we set the prior distribution in the Bayesian setup to be the initial condition for the first rho, if we set the direct mass at the observation to be the initial condition for the last line for rho, and then solving rho is the same with solving the posterior distribution. So to sample from the posterior distribution is the same with sampling this function rho. Then we can have some algorithms called HJ-sampler. Assume the underlying process is an SDE. Then we have the training stage. That is, the goal is to get the control. So getting the control, there are different ways to get the control. You can solve HJB. You can use some more data-driven way using the score-based generative model, diffusion model, or you can use HJB using Riccati equations to solve HJB. There are so many solvers for the first step. And as long as you get the control, then you get the samples by sampling from this controlled SDE. That's the second step. That's the inference step. So this is an illustration of how we use the diffusion model in this algorithm. In the training step, we generate sample paths. Those are the training data by getting from samples from the prior distribution and evolve those samples according to the underlying SDE. And then for the inference step, after we train the neural network, which is the control, remember score function is the same with the control. After we train the neural network in the first step, after we get the control, now we can start from your observation points, run your simulator for the control SDE, then you get those paths, those are the samples from the posterior distribution that we want in this Bayesian inference problem. Now let me just quickly show you some numerical results of the paper. We test the algorithm on 1D Brownian motion. So we assume the underlying stochastic process is a 1D Brownian motion. Then for 1D Brownian motion, you can And then we assume the prior distribution is a standard Gaussian. And now everything is Gaussian, so we can have the underlying distribution, the ground truth. So we can compute the error. Now, the first table is the W1 error of the posterior samples of the problem setup. Now you can see analytical one is the algorithm when we solve HJB equation analytically. Because everything is Gaussian, you can get the solution of HJB equation easily using quadratic function. So the first row is the errors for HJ-sampler when the control is obtained without error. The second row is the error for the HJ-sampler when the control is obtained by neural network, diffusion model, SGM. And we also have different error and running time at different problem setup. So you see the error is almost like 10 to the negative 3 for analytical thing, and 10 to the negative 3 or 10 to the negative 2 for the neural network thing. So this means the algorithm should work at this level accuracy. And we also test on the underlying distribution for Brownian motion with the prior distribution to be a mixture of uniform. We know if we do MCMC style sampling, when you have a prior distribution like this, you have two separated supports of distribution, then it's kind of hard to do the sampling. But if you see from the figure, the dashed line is the ground truth, and the colored region is what we get from samples. So you see they align pretty well, and the support align pretty well. So that means this solver can also handle the case when your distribution has different supporting domain. And we also tested on the nonlinear model misspecification. So we assume we get an underlying ODE, but we don't know some term on the ODE, and then we get the data, try to infer the ODE solution, and we also get some numerical results. Due to the time, and I would like to skip this part. If you are interested, we can talk later, or you can refer to the paper. It's on the archive. So let me just give a quick summary, and we can wrap up here. So this is a paper that tries to emphasize the connection. So we have different mathematical tools, AI tools, and we try to bridge those tools together to have this more abstract view. We have the connection between the diffusion model, PDEs, stochastic optimal transport, or mean field games, optimal control, everything related using the log transform. And having this more broader view, more abstract view can help us, as long as you get some related problem, it can help us to get different versions of AI, and then different versions of neural network, different loss function, different architectures, how you get the data, and in a plug and play way. And then it can be used to design different machine learning methods for the related problems. And more generally, because this connection is not restricted to the Brownian motion, it is not restricted to Laplace operator, we can have more complicated stochastic process like Levy process random walk, which may be suitable for design different diffusion models. And also, because of this more abstract level of theory, you can easily get different versions, different variations of those diffusion models. You can have guided version and try to play with the density a little bit. And we have the preprint available online. And a little bit advertised for myself. I'm currently working at Hamilton Robotics. And we are doing the control for robot fleet. So, and I cannot give a lot of details here, but I'm happy to talk offline. The reason why I feel it is a very good practical problem setup for this community is, firstly, we use L1 distance. Stan said L1 distance is the distance that we use at UCLA, so it is a UCLA thing. The whole map is a grid-based map. So when your robots moving on this map, you are using Manhattan distance, L1 distance, and everything is so related. And second thing, we have so many robots. So the number of robots is somehow like mean field. So when you have this large number of robots, it's hard to do multi-agent optimal control because the dimensionality will be too high. The mean field may be a good thing. So it's connected to mean field. And then thirdly, we're handling the movement of the robot fleet. So doing the path planning, path control, everything. So I feel it's so related, and but it's not a simple application. So there is still some gap between the industry level application with the mathematical model, and this gap has some difficulty in solving the industry problem using our method directly. So there is still something to be done to fill in this gap. So that's why I feel there may be some possibilities to discuss scientific problems or related to industry applications. So this is a little advertisement for myself. If you are interested, we can discuss offline. Please contact me at this email. Okay, thank you so much.